let's finish this chapter up here. So we're going to very briefly talk about solids. I'm going to skim through what could be an entire bachelor's degree's worth of material in about, I don't know, 6-7 minutes. So please do not think that this is an exhaustive review of X-ray crystallography or crystal lattice unit cells. We are truly skimming only the very surface and looking at the simplest of examples with each of these things. So, just really briefly here, X-ray crystallography is actually an incredibly useful tool that is used for a few different things actually. It's mostly used to determine the identity of unknown solids that you might find. So if you worked for an oil company, for example, and somebody was drilling and they found some material and they don't know what it is, one of your options for determining what that material is to put it in an X-ray crystallographer, blast it with some X-rays, and see what the diffracted X-ray pattern gives you. Because there's a library, essentially, of the patterns that you get when you shoot X-rays into a crystal like this, and they are essentially a fingerprint for that material. Now again, I am dramatically simplifying this process, but you get the main gist of what happens here. Is you have this crystal, you shoot some X-rays in, the X-rays will bounce off of these the atoms in the crystal, and based on the location of the atoms in the crystal, you will get different diffracted X-ray patterns on the detector. And again, that's very much like a fingerprint, where you can tell what you have based on the diffracted X-ray pattern. So what you're looking at with that X-ray crystallographer is you're really trying to figure out what we call the crystal lattice, or the unit cell of the crystal lattice. And what a unit cell is it's just the smallest unit that shows the entire pattern of the material. So unit cells are made up of what we call lattice points and lattice planes, and every particle that exists in that unit cell exists at one of these lattice points. So, or conversely, you could say that either the particles are at the lattice points or the lattice points are at the particles. It doesn't really matter which way you say it. But as you can see here in this very simple example of a unit cell, this is the simplest unit cell possible. We have lattice points at each of the corners of a normal box here, normal six-sided box. And so each of those little corners is an eighth, I believe, of an atom, which we'll get to in just a second. But each of these points is a lattice point. Each of these corners here is a lattice point, and then each of the planes of the box is a lattice plane. And so the whole idea of this unit cell is that if you take this simple cubic unit cell as an example, and you just copy and paste it a million times and just arrange them next to each other so that they're sitting and just right next to each other, that will give you the actual structure of the crystal itself. So it's the simplest way of representing the crystal structure, where if you just copy what you have, it gives you the whole structure. And there's lots and lots of different kinds of these unit cells. The one we just looked at, like I said, is the simplest one possible. It's what we call a simple cubic unit cell. So the atoms are arranged in the simplest way possible. All the angles are 90 degrees. All the sides of the cube are exactly the same length. It is as simple as it can possibly be. But you can have unit cells where one side is longer than the other, or one side is shorter than the other two. You can have ones where none of the sides are the same length. That's what we call an orthorhombic, that all the angles are still 90 degrees. You could have none of the sides be the same length, and only two of the angles are at 90 degrees to one another. You can have hexagonal, where two of the sides are the same, but one of them is different. Two of them are 90, one of them is 120. Like there's many, I'm not going to go through the rest of these, but there's many different shapes of unit cells. We're going to look at just a few of the most simple ones here. This one we have actually already seen, and it is an eighth. Yep, so I was right there. So we have an eighth of an atom at each corner, and because there are 8 corners, this simple cubic unit cell actually contains 1 atom worth of material. Now it does not contain 1 single atom, but when you add all the individual parts of the 8 different atoms together, you get 1 atom worth of material. A body-centered cubic unit cell is very similar because it still has that eighth of an atom at each corner, but instead of just being empty in the middle, we actually put in a different atom right in the middle of the unit cell. And so this actually has 2 atoms in it. Again, 8 corners, 1/8 of an atom at each one of those, and then a whole atom in the center gives us 2 atoms. This is a slightly more dense unit cell. There's a whole lot of empty space in this simple cubic unit cell. This one is a little bit more dense. And the face-centered is even more dense. So the face-centered cubic unit cell, now instead of having an atom at the center of the unit cell, we have 6 half atoms at each of the faces, but we still have those 8 atoms at the 8 corners of the box. And so this actually has 4 whole atoms worth of material in it. Alright, so you might notice there that we're kind of making our way from very low density crystal packing structures, and now we are up to what is actually the most dense way of packing spheres, which, as we'll see in just a second, is called hexagonal close packing, I believe is the full term. But anyway, let's say we want to pack these spheres in as tightly together as possible. Well, the first thing we would do is we would not line them up like we did back here. We wouldn't put them to where the diameters of the spheres are lining up with each other. We would offset them because they can fit in closer to each other that way. So if we offset each row from the next, and then we take another layer of atoms, and not only do we offset the atoms in that layer as well, but we then offset the layers from one another. So we don't place one atom directly on top of another atom. We offset the entire layer itself so that the atoms in one layer sit in the indentations of the layer below it. This gives us the hexagonal closest packing structure, which is the tightest way that you can pack spheres that are of similar shape anyway. I'm sure there's ways you can pack spheres in if you have dramatically different sizes, but when it comes to spheres that are similar in shape or exactly the same shape, this is as close together as you can possibly get it. So the very dense solids that you might come across that are very heavy, they probably have some packing structure similar to this. So again, this is hexagonal closest packing. Last thing here, just a quick thing about classifying solids. You can have molecular solids, which are things that we're very familiar with. This is where we have a solid that's just made up of molecules. So ice would be an example of this, because it's just made of water molecules. You can have ionic solids. These are composed of ionic compounds or ions. So table salt would be like that. And so we're decently familiar with those two. But there actually are a few different kinds of atomic solids that you've probably not heard about or not have pointed out to you. We can have non-bonding atomic solids where the material is only held together by dispersion forces. So these are materials that would only exist at extremely cold temperatures for the most part. Some are not quite that way, but for the most part. Metallic atomic solids are very, very common. These are actually held together by what we call metallic bonds, which again, you could have a whole class over metals and how they bond together and how electrons behave in metals, but I'm just going to tell you that there is a special way that metals are bonded together. They essentially act like one large atom, in a sense, where the electrons flow around the entire solid, almost like a fluid. And then the last one there is the network covalent atomic solids, and these are held together by covalent bonds. These tend to be extremely strong materials, like diamond or quartz. These are things that are held, they're a solid, they're just a single type of material, and they are held together by covalent bonds instead of metallic or dispersion forces. So just wanted to point those out because I do believe it will pop up in the homework. I think you might have to classify a few things into one of those categories. So I wanted to point those out. But that is the end of the chapter. So please be sure, if you have not already, please be working on the homework and get those done. If you have any questions, feel free to let me know. And I will talk to you all again in chapter 11.